Hi everyone, welcome to the section on activation functions. So in this section, we will learn why activation functions are important for neural networks and how they can improve the performance of the neural network. So these are the topics which we are going to cover in this section. First, we will learn how the perceptron, which is a simple neural network, can be used to perform the classification. So in this topic, we will see how perceptron can be used to perform the linear classification. Then we will study why we need activation functions for neural network. So we will see in order to learn the non-linear pattern in the data, we need activation functions. That is, if we want our neural network to perform non-linear classification, we need activation functions for the neural network. Then adding activation functions to neural network. So in this particular topic, we will see where we need to add the activation function. That is, either activation function is important for hidden layer or the output layer or both of the layers. So here in this topic, we will discuss where to add the activation functions to the neural network. Then we will discuss first important type of the activation function, that is the sigmoid activation function. Then we will discuss the tangent hyperbolic activation function, and we will see how this activation function is different from the sigmoid function. Then at the last of this section, we will study two more important activation functions, that is the ReLU and a leaky ReLU function. So ReLU and leaky ReLU function are most commonly used activation functions in neural network. So I hope you will enjoy this section. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn how we can perform classification with the help of the perceptron. So perceptron is considered as the simplest form of the neural network. So let's start with the application of AND gate implementation. This is our AND gate. The property of AND gate is that it produces output which is equals to 1 only if both of its inputs are equals to 1. Otherwise, it will produce 0. Okay. Here is the truth table of the AND gate. We can see that when x1 and x2 both are 0, it is producing 0. Similarly, if any of the x1 and x2 is 0, it is also producing 0. And it is producing 1 only when both x1 and x2 are equals to 1. So this is the truth table of AND gate. And we are going to use this truth table as our simplest form of dataset in order to learn that how we can perform classification with the help of perceptron. So this is a 2D representation of the AND gate. We have first dimension x2 and we have second dimension x1. Now we have to plot this AND gate in 2D. Okay, so in our first point, in our first data sample, we can see that x1 and x2 both are 0. So here is the point. This is the point where both x1 and x2 are 0. Now look at the second point. In the second point, x1 is equals to 0 and x2 is equals to 1. So we are here basically where x2 is equals to 1. This is the x2 axis, and here x2 is equals to 1, and at this point x1 is equals to 0. Now look at this point. At this point x1 is equals to 1 and x2 is equals to 0. So this is our third data sample. This is our fourth data sample where both x1 and x2 are equals to 1. Now if we see, we have two kind of classes, that is 0 and 1. First three data samples belongs to class 0 and the fourth data sample belongs to class 1. So here those samples which belongs to class 0 are denoted with light blue color, and the sample which belongs to class 1 is denoted by light green color. Now the question is, can we separate both these classes with the help of a straight line, or is there any possibility that we can draw a decision boundary in the form of straight line that can separate both these two classes, that is 0 and 1? So answer is yes, there is a possibility of a straight line that becomes a decision boundary that can separate class 0 from class 1. It means AND gate is a linearly separable gate. That is, AND gate can be separable with the help of a straight line. That is, the classes in the truth table of AND gate can be separate with the help of a straight line, which becomes the decision boundary for the AND gate. Now the question is, can we use perceptron for this kind of classification? Let's understand this. This is our perceptron. and the two inputs to the perceptron are x1 and x2, and the bias is equals to -1. Okay, so the weights associated with both x1 and x2 are equal and their value is 1. So in this way, we will see how we can use this perceptron in order to perform the classification for the AND gate. So this y represent the output or the predicted value of the perceptron. So y is equals to w1 x1 plus w2 x2 plus bias value. So here perceptron is performing an addition, and these three branches are input to this perceptron and it is adding them. So the first value is x1 w1, then we have x2 w2 plus b. So this is the equation at the output of the perceptron. Let's decide about the conditions for the classification. So the conditions are very simple. So we have decided that if w1 x1 plus w2 x2 plus b2, that is the output of perceptron, will be greater than 0, we will call it as a 1. And if the output will be equal or less than 0, we will be equal to 0, or we will equate it equal to 0. So this is the conditions of classification. Let's see whether it is able to implement AND gate or not. So let's start the implementation. So our output equation of the perceptron is w1 x1 w2 x2 plus b. Okay, put the first data sample. The case one mean we are going to put the value of the first data sample. For first data sample, both x1 and x2 are 0. Therefore, both these terms will be 0, and we will get only -1, which is the value of a bias. That is, this is the situation. Both of the first terms are 0 and we will get -1. Since -1 is less than 0, therefore, according to the classification condition, we get 0. It means that our perceptron has classified first sample correctly. That is, when both the input are 0, it is giving a 0 label here. Now case 2. Case 2 means passing a second data sample to the perceptron. Here x1 is equals to 0 and x2 is equals to 1. So if we pass x1 is equals to 0, the first term will be 0. We can see that the first term is 0. Since w2 and x2 both are equals to 1, therefore we will get 1 at the second term. The bias is -1. So +1 -1, we will get 0. If we get 0, it will be equals to 0. So we can see that for the second data sample, the bias has classified it correctly. Now let's see about the third data sample. Now for the third data sample, now x2 is equals to 0. So this term will give us 0. Here we can see that this term will give us 1 because both w1 and x1 are 1 and our bias is -1. So +1 and -1, we will get 0. So according to classification condition, we get 0, and we can see that the third data sample is also classified correctly by our perceptron. Now pass the last data sample to the perceptron. For last data sample, both x1 and x2 are equals to 1. So we will get 1 here, and -1 here. So we can see that 1 + 1 -1 is equals to 1. 1 is greater than 0. Therefore, we will get 1 at the output. So we can see that our perceptron has classified all the data samples of AND gate correctly. It means perceptron can be used as a linear classifier. So we have observed here that the perceptron can be used as a linear classifier and it can separate the classes. So in this lecture, we learn with the help of AND gate implementation, that is, perceptron can be used in order to perform the classification. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are again going to learn how to perform classification with the help of perceptron. In the previous lecture, we learned how to perform classification with the help of perceptron using AND gate implementation. Here we are using another example, that is OR gate implementation. OR gate is different from the AND gate. This is the truth table of the OR gate. We can see that OR gate produce 1 if any of the input is equals to 1. Look at the second data sample. Here only x2 is equals to 1. Therefore, we are getting 1. Here only x1 is equals to 1 and we are getting 1 at the output of the OR gate. Here both the inputs are 1 and we are getting 1 at the output. Only at the first data sample it is happening that both of the inputs are 0. Therefore, we are getting 0 at the output of the OR gate. So OR gate is the gate which produces 1 at the output if any of the input is equals to 1. So this truth table of the OR gate, we will use this truth table as our data set for classification. So here we are implementing OR gate in 2D. This is our x1 dimension and this is our x2 dimension. Now look at the first point. The first data sample has both values equals to 0. That is x1 is equals to 0 and x2 is equals to 0. So this is our first data sample and it belongs to class 0. Now this is our second data sample. In second data sample, x1 is equals to 0 and x2 is equals to 1. So this is our x2 axis or x2 dimension. So this is our second data sample where x2 is equals to 1. This is our third data sample where x1 is equals to 1. So we can see that here x1 is equals to 1 and this is our fourth data sample where both x1 and x2 are equals to 1. So we can see that here x1 is equals to 1 and x2 is also equals to 1. Now out of these 4 points, only 1 point belongs to class 0 and the last 3 data points belongs to class 1. So the sample belongs to class 0 is denoted here by light blue color, whereas the sample belongs to class 1 are denoted by light green color. Now the question is, can we draw a straight line in order to perform the classification? So the answer is yes. We can draw a decision boundary in the form of straight line that can separate a 0 class from class 1. So in this case, we have learned that OR gate is also a linearly separable gate. That is, the data points in OR gate can be separate with the help of a straight line. Now let's see how we can implement this with the help of a simple perceptron. So this is our perceptron. This is our simple neural network and we are going to implement the OR gate. Now if we see this circuit and that neural network which we use for the implementation of AND gate, there is only one difference and that difference is the value of a bias. When we use a neural network in order to perform AND gate implementation, the value of bias was -1. Here we are using the value of bias is equals to -0.5. Rest everything is same. That is x1 and x2 are two input to this perceptron and w1 and w2 are the weights associated with these input and the value of each weight is equals to 1. So if we want to write the output equation of this perceptron, it is w1 x1 plus w2 x2 plus b, that is the value of a bias. So the conditions of classifications are same which we set in our previous example, that is for AND gate. That is, if w1 x1 plus w2 x2 plus b is greater than 0, we will assign y is equals to 1. Similarly, if it is equal or less than 0, then we will assign 0 to y value. Let's see how we can use this simple perceptron in order to implement OR gate. So this is the truth table of our OR gate, or this is our data set. This is the output equation of the perceptron and these are the conditions of classification. Let's pass first data sample. So in case 1, when the input is 0, 0 means we are going to pass first data sample to the perceptron. So x1 is equals to 0, x2 is equals to 0 and the value of bias here is -0.5. So this term will be 0 due to x1, this term will be 0 due to x2 and we are left with only -0.5. So we can see that in case 1, we are left with only -0.5 which is less than 0. Therefore, we assign 0 to our y. So when both inputs are 0, our perceptron is also predicting a value 0. It means the first data sample is correctly classified by the perceptron. Now look at the second data sample. In the second data sample, the x1 is equals to 0 and x2 is equals to 1. So this is the situation. Due to x1, which is 0, the first term will be 0. And since w2 and x2 both are equals to 1, so we will get 1 at the second term. This is the value of a bias. So 1 minus 0.5, we will get 0.5. 0.5 is greater than 0. So according to our classification condition, we will get 1. So we can see that for the second sample, our perceptron is predicting 1, that is the second sample is also correctly classified. Similarly, for the third sample, we will again get the value of 0.5, which is greater than 0, and we will get a value of 1 according to our condition of the classification. So it means the third data sample is also classified correctly by our perceptron. Now look at the case 4, that is about the fourth data sample when both the inputs are equals to 1. So here W1 and X1 both are equals to 1, W2 and X2 both are equals to 1, and this B is equals to minus 0.5. So it is 1 plus 1 minus 0.5. If we solve this, we will get 1.5, which is greater than 0. And we know that according to the condition of classification, if we get greater than 0 value, we will assign a label 1. So we can see that with the help of this perceptron, we can easily implement the OR gate, or we can perform the classification on the OR gate. So in this lecture, we learn again that the perceptron can be used to perform a linear classification. In this lecture, we use OR gate implementation. In the previous lecture, we used AND gate implementation. So with the help of AND gate and OR gate implementation, we have proved that a simple perceptron can be used to perform classification. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn why we need activation functions in neural network, why they are so important for the neural network. Now let's understand the importance of the activation function with the help of a XOR gate. Now this is a different from the OR gate. It is called XOR gate, XOR. Okay, so the property of the XOR gate is that it produces 0 if all the input to the XOR gate are similar. If we see the first data sample and the last data sample, the label assigns are 0. The reason is that in first data sample and in the last data sample, both of the inputs are same. In the first data sample, both inputs are 0, and in the last data sample, both inputs are 1. So the property of a XOR gate is that it will give us a 0 if both of the inputs are same. When the inputs are different, that is 0, 1 or 1, 0, we are getting 1 at the output of the XOR gate. So this is the truth table of the XOR gate. Let's plot this truth table of a XOR gate in 2D. So here is the 2D implementation of this dataset, or the truth table of the XOR gate. Okay, so when both inputs are 0, that is when x1 is equals to 0 and x2 is equals to 0, we are here. Okay, when x2 is equals to 1 and x1 is equals to 0, we are here. Here we can see that this axis belongs to x2, and here the value of x2 is equals to 1. So this is our second data sample. This is our third data sample where x1 is equals to 1 and x2 is equals to 0. Okay, and this is our fourth data sample where both x1 and x2 are equals to 1. Now, these 4 data samples are equally divided between two classes, that is 0 and 1. So those data samples which belongs to class 0 are represented here by green color, and those who are represented with the light blue color belongs to class 1. So this is our class 1, this is our class 1, this is our class 0, and this is also class 0. Now the question is there any possibility that we can draw a straight line in order to separate these two classes? So we have class 0 and we have class 1. Can we draw a straight line anywhere in this 2D representation where we can separate both the classes? So the answer is no. For the XOR gate, we cannot perform a linear classification because XOR gate is not linearly separable. Like these two classes these two sample belongs to one class and these two sample belongs to other class. So if we want to perform the classification here, we need something like that, which is a non-linear. We can see that if we draw the classification boundary like this, in that case, these 2 points are on one side of the classification and these 2 points are on the other side of the classification. So this is non-linear classification. in order to perform the nonlinear classification with the help of perceptron, we have to make perceptron to learn the non-linearities present in the dataset. That is, in addition to the linear properties, we make our perceptron learn the non-linear properties which are present in the dataset or the non-linear patterns which are hidden in the dataset. So in order to make perceptron to learn non-linear hidden pattern in the dataset, we need activation function. So why we need activation function? Our real world data is non-linear and therefore it is not linearly separable. So we use activation functions to make our neural network to learn the non-linearity and the complexity of the data. So we can see that we can easily perform the linear classification with the help of a neural network or with the help of a simple perceptron. But if we want to make non-linear classification, in that case, we need activation function. So activation function help neural network to learn the non-linearity and complexity of the data. And later on, this will help neural network to perform non-linear classification. So this is the situation for which we require activation function in neural network. Here we have a simple condition where the dataset is linearly separable. Here the dataset is not linearly separable. Therefore, in this case, we need neural network, activation function in the neural network. If we see this equation of the neural network without the activation function, so the equation is W1x1 plus W2x2. So here the output of this neural network is W1x1 plus W2x2. Now, if we compare this equation with the equation of multiple linear regression, then both equations are very much similar. The only difference is if I add a bias term here, then these two equations become exactly equal. Okay, so it is W1x1, it is W2x2. Here we can see that W1x1 and W2x2. It means the equation of a neural network is a linear equation without the activation function. So till now, we have discussed the importance of the activation function, but we did not add any activation function yet in our neural network. And we can see that without the activation function, the output equation of a neural network is a linear equation. So in order to make this equation non-linear so that our neural network can learn the non-linearity present in the dataset and can perform non-linear classification, we need to add the activation function in our neural network. So I hope you understood the importance of an activation function in the neural network. So in this lecture, we learn that the equation or the output equation of a neural network is similar to the linear regression equation without activation function. And without activation function, we cannot perform non-linear classification with the help of neural network. So activation function are very important in order to improve the performance of the neural network. They help neural network to learn the non-linearities present in the dataset so that they can perform non-linear classification. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn how to add activation function in a neural network and what are the layers where we need to add activation functions. So this is our neural network without the activation function. And we can see that the equation of a neural network is a linear equation without the activation function. So this is the input layer of the neural network. This is the hidden layer of the neural network. And this is the output layer of the neural network. So we need activation functions at the output of the neural network and at the hidden layer of the neural network. When we have to make a decision, then we need activation function at the output layer of the neural network. And in order to make neural network learn about the non-linearities present in the dataset, we need activation function at the hidden layer, because hidden layers are used for learning and the output layer is used for the decision, that is to perform the classification or regression. So here we can see that we have an activation function with the output layer. So that activation function is going to be used to model the output of a neural network, and it helps neural network to make decision about the classification or the regression. So we need activation function with the output layer of the neural network. So here we have the activation function in the form of threshold, and we can see that it is with the output layer of the neural network. Here we can see that we have an activation function which is a sigmoid function, and here we are using the activation function with the hidden layer. So here first hidden layer has learned the linear property of a data set, and then we add the activation function with the hidden layer so that hidden layer can also learn the non-linearities present in the data set. And then we have an output neuron, and then after output neuron, we also need the activation function in order to perform either classification or regression. So we see that we need activation function both with the output layers and with the hidden layer. The activation functions with the output layers are used to perform the classification or regression problem, and the activation functions used with the hidden layers are used to make hidden layer learn about the non-linearities that is present in the data set. So this is the activation function that is being used with the hidden layer. So we can see that we have add another layer. This is kind of another layer which is an activation function. So when we implement neural network in the coming section in PyTorch, we will see that we need to add a separate layer for the activation function. But when we draw a diagram, when we represent a neural network in the form of a diagram, we do not need the separate layer in order to show the activation function. So this is the internal visualization of the neuron. So if we divide the neuron in two portions, so that is the input side of the neuron, and this is the output side of the neuron. So we can apply activation function at the output side of the neuron. We can see that this phi is an activation function, and we are applying at the output side of the neuron. So when we draw a diagram, we do not need to draw a separate layer which shows the activation functions. However, when we will implement neural network in PyTorch, in that case, we need to add activation as a separate layer. But here we can see that we can inject the activation function in the same neuron, whether it is the output neuron or the neuron present in the hidden layer. So this is the input side, which is collecting the inputs from the input layer, and this is the linear learning. After that, we are passing this learning to the activation function to make it non-linear. So this is the output of this neuron after the activation. So this is phi, and this is called the activation function. So we see that in this lecture, we learn that we need activation function with the output layer and with the hidden layer. When we use activation function with the output layer, it is used to perform classification or regression. And when we use activation function with the hidden layer, it is used to make hidden layer learn about the non-linearities of the dataset. So I hope you understood this lecture. I hope you understood how to add activation function, and I hope you understood what are the layers where we need to add activation functions. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the sigmoid function when it is used as an activation function. So sigmoid is an important activation function, especially when it is used with the output layer of the neural network. So this is sigmoid function. This is the mathematical representation of the sigmoid function. This is the equation of the sigmoid function, and this is the visual representation of the sigmoid function. So we can see that the minimum value of the sigmoid function is 0. The maximum value of the sigmoid function is 1. Okay, if we pass 0 to the sigmoid function, it will give us the value which is equals to 0.5. It means the output of the sigmoid function is 0.5 if the input to the sigmoid function is 0. If we pass a large negative value to the sigmoid function, it will give us a 0 value. Similarly, if we pass a large positive value, we will get the output of the sigmoid function which is equals to 1. So the minimum value of the sigmoid function is 0 and the maximum value of the sigmoid function is 1. So it is used to suppress the input between the range of 0 and 1. So this is some mathematics which is involved with the sigmoid function. So this is the equation of the sigmoid function. If I put x is equals to 0 here, what will happen? When we put x is equals to 0, it will become exponent raised to power 0. And we know that anything raised to power 0 is equals to 1. So 1 plus 1 becomes 2. So we will get a value equals to half. It means if the input to the sigmoid function is 0, the output of a sigmoid function is 0.5. If we pass a very large negative value to the sigmoid function, which is here minus infinity, then if I put x is equals to minus infinity, then this minus and this minus will become plus, and I will get exponent raised to power plus infinity, which is equals to infinity. And if we add any number to the infinity, we will get infinity. And 1 divided by infinity is equals to 0. It means if we pass a large negative number to the sigmoid function, we will get 0. Similarly, if we pass a large positive number to the sigmoid function, if we put x is equals to plus infinity here, we will get minus infinity. Then exponent raised to power minus infinity will becomes 1 over exponent infinity. Anything raised to power infinity is infinity, and 1 over infinity is equals to 0. So it will become 1 over 1, which is equals to 1. So we can see that the minimum value of the sigmoid function is 0. The maximum value of the sigmoid function is 1. And if we pass 0 in the sigmoid function, we will get 0.5. So these are a few properties of the sigmoid function. The first property is it is not good for hidden layer when there are more than 2 layers in a neural network. That is, if we have more hidden layer in the neural network, it is not a good idea to use sigmoid as an activation function with the hidden layers. So in the next slide, we will see why it is not a good idea to use sigmoid function with the hidden layers. Its minimum value is 0 and maximum is 1. Therefore, it is good for classification layer. It gives us the classification probabilities of classes. So the minimum and maximum value of the probability is also 0 and 1 respectively. Similarly, the minimum and the maximum value of the sigmoid function is also 0 and 1. Therefore, a sigmoid function can be used with the classification layer or the output layer of a neural network. It can give us the classification probabilities of the classes. The third property is the sigmoid has the biased average. This means the average of its input is 0, but the average of its output is 0.5. Now, if I pass two values to this sigmoid function, the one value is minus 10 and the other value is plus 10. Okay, so the average of minus 10 and plus 10 is equals to 0. It means the input to the sigmoid function, the average value of the input to the sigmoid function is 0. But what we will get at the output? For minus 10, we will get 0, and for plus 10, we will get 1. And mean of 0 and 1 is 0.5. So this means that the output of the sigmoid function is biased and the input of the sigmoid function is not a bias. That is, the sigmoid function produce the biased average value of the output. So in that way, this is the reason that the sigmoid function is a non-linear function, because it maps the input function into a non-linear space. That is the reason that sigmoid function is a non-linear function. Now, why it cannot be used with the hidden layer? So this is the reason. If we see the visualization of the derivative of the sigmoid function, so the derivative of the sigmoid function is 0.25. This is the derivative of the sigmoid function, and this is the actual sigmoid function. If we see the derivative of the sigmoid function, its maximum value is 0.25. So what will happen? We know that the hidden layers are used for learning, that during backpropagation, we will have the derivatives of the term. In the previous section, we got a gentle introduction of the backpropagation. We will learn in detail about the backpropagation in the coming sections of the course. But we know that in the backpropagation, when we write the equation of the backpropagation, we need gradients or derivative. So the derivative of the sigmoid function is 0.25. So if we need to multiply 0.25 more than one time, our value becomes close to 0. Here is the example. Here 0.25 is multiplied by 3 times. So its value is close to 0, that is 0.016. If we keep on multiplying 0.25 with each other, we will get a 0 value. So if we get a 0 value during the backpropagation or during the learning of a neural network, our neural network will not learn, and that problem is called vanishing gradient problem. Now the gradient are the derivatives which we use in order to write the backpropagation equation. So in backpropagation equation, we saw in the previous section where we learn about the basic of backpropagation that we have the gradient equation like dE by dy, dy by dH1 or dE by dW1. So that derivatives are multiplied with each other. And if we use sigmoid as an activation function, the derivative of the sigmoid will become a very small quantity, and if we keep on multiply these small quantity, we will get zero during the back propagation, which is one of the most important stage of the learning of neural network. So if we use sigmoid function with the hidden layer, then we will face a problem which is known as vanishing gradient problem. That is, our gradient will die out during the back propagation. And if our gradient die out during the back propagation, there will be no learning in the neural network and the performance of neural network become worse. So that is the problem with the sigmoid function, due to which we do not use sigmoid function with the hidden layer. We use sigmoid function as an activation function only with the output layer so that we can perform classification. So in this lecture, we learn about the sigmoid function. We learn why sigmoid function is useful activation function when used with the output layer of neural network, and what are the problems of using sigmoid as an activation function with the hidden layer. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will discuss another activation function, which is hyperbolic tangent function. So this is hyperbolic tangent function. We can see that this is the mathematical representation of the hyperbolic tangent function. Here we can visualize the hyperbolic tangent function. So we can see that its minimum value is -1 and its maximum value is +1. Sometimes it is considered as an extension of the sigmoid function, because the minimum value of sigmoid is 0 and the maximum value is 1, but here the minimum value has been extended to -1. So its minimum value is -1 and the maximum value is +1. So this is hyperbolic tangent function, and this is the mathematical equation. When we pass input equals to 0 to the hyperbolic tangent function, we get 0. So we can see that its output is 0 when the input is 0. And when we pass a negative value to the tangent function, we also get the negative value at the output. Similarly, when we pass the positive value, to the tangent function, we will get the positive value at the output of the tangent function. So it gives 0 at 0, and it gives negative value when the input to the tangent function is negative. Similarly, it produces positive value if the input to this hyperbolic tangent function is positive. So this is the property of this hyperbolic tangent function. So these are another properties of the hyperbolic tangent function. It is somehow okay for hidden layer. So why it is not good for the hidden layer? We will discuss it very soon. Okay, its minimum value is -1 and maximum value is +1. Okay, it doesn't have the biased average. This means that the average of its input and output is 0. If we remember, in the previous lecture, we discussed the sigmoid function. The sigmoid function has biased output average because its minimum value is 0 for sigmoid and maximum value is 1. So if we take the average of 0 and 1, we will get 0.5. But in case of hyperbolic tangent, we have unbiased average because its minimum value is -1 and its maximum value is +1. Therefore, we will get 0 at the output of the tangent function, the average value of 0 at the output of the tangent function. Therefore, it has unbiased average. So what is the advantage of the unbiased average? So here is the advantage of unbiased average. So what happens when we use this activation function with the hidden layer? The mean of the hidden layer comes out to be 0 or very, very close to 0. Hence, tangent hyperbolic function helps in centering the data by bringing mean close to 0. So what happens when it is used with the hidden layer? Then during the learning of the hidden layer, the data becomes mean centric, which is approximately equals to 0, due to which the learning for the next layer becomes easier and the training of the neural network becomes faster. So what happens, instead of sigmoid function, if we use hyperbolic tangent function with the hidden layer, the speed of the neural network becomes faster because it will be easy for the hidden layers to learn. So this is the advantage of unbiased average or unbiased mean. Now, this is the problem associated with the hyperbolic tangent function. That's why it is somehow okay with the hidden layer. The problem is the same as that with the sigmoid function. That is the problem of vanishing gradient. If we see the derivative of the hyperbolic tangent function, so this yellow line indicates the derivative of the hyperbolic tangent function. So at equals to 0, when the input is 0, or at x is equals to 0, its value is 1. But what happens? The gradient becomes 0 when we move in the negative direction, and also 0 when we move in the positive direction. So it is 1 when the input is 0, but for the negative inputs, it is close to 0, or it is starting to become 0. And similarly, for the positive value, the gradient becomes 0, due to which during the learning, there are high chances that gradients become die out, or a vanishing gradient problem occurs. Due to vanishing gradient, the learning of the neural network decreases, and it could not generalize well on unseen data. So it has the same problem as that of the sigmoid, that is the vanishing gradient problem, due to which we do not use them so often with the hidden layer. So I hope you understood the hyperbolic tangent function as an activation function. It is somehow the extended version of the sigmoid function, and it has the advantage that it has unbiased average. On the other hand, it has the problem which is same as that of the sigmoid function, that is the problem of vanishing gradient. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will discuss two more important activation functions, that is ReLU and a leaky ReLU. So let's start this lecture with ReLU function, which is rectified linear unit. So ReLU is the abbreviation of rectified linear unit function. Okay, so here we have a ReLU and the derivative of a ReLU. We can see that this light blue line is our ReLU function, and this yellow line is the derivative of the ReLU function. If we see the ReLU function, it is 0 before 0. That is, for any value which is negative, it is 0. That is, if we pass a negative value to the ReLU function, it will give us a 0. On the other hand, if we see, it has a constant slope for any value which is greater than 0. That is, if we pass 2 to the ReLU function, it will give us 2. If we pass 4 to the ReLU function, it will give us a value equals to 4. So for positive value, it will preserve the value. But for the negative value, it will give us a 0. So if we see, this is the mathematical representation of a ReLU function. So its equation is maximum of 0 and x. So if x is equals to negative, in that case, x becomes less than 0, and the ReLU function will select 0. On the other hand, if x is a positive number, in that case, the ReLU function select that positive number. So it preserves the positive number, and for negative number, it will give us a value equals to 0. So this is the property of a ReLU function. We can also see that this ReLU function is a piecewise linear function. Overall, it is not a linear function, but it is a piecewise linear function. If we see, before x is equals to 0, its slope is 0. It is a straight line, but its slope is equals to 0. And after x is equals to 0, its slope is constant. So it is linear with slope 0 before 0, and it is linear with the constant slope after x is equals to 0. So it is piecewise linear because throughout its slope is not constant. Its slope is changing throughout its progression. It means it is a piecewise linear. Here is a discontinuity at x is equals to 0. So this discontinuity make ReLU function a non-linear function. Now this is a ReLU function. We can see that if a negative value is passed through a ReLU function, it is giving us a 0. But if a positive value is passing through a ReLU function, it is preserving the positive value. So this is the advantage of a ReLU function. The other advantage is, if we see the derivative of the ReLU function, it is 1 for all the positive value. It means it is better than the sigmoid function and the hyperbolic tangent function, because its derivative is 1 for all the positive values of x. In that case, there is very less chance of a vanishing gradient. Due to this reason, these days, the ReLU function is the most commonly used function in neural networks. So these are the properties of a ReLU function. So we have discussed already that it is a piecewise linear function. It has the discontinuity at x is equals to 0. That is, before x is equals to 0, it has a different slope, and after x is equals to 0, it has a different slope. This makes it a non-linear function. The second important property is it preserves the positive input and transform negative input to 0. It has a linear slope of magnitude 1 after x is equals to 0. So its slope is constant, which is equals to 1 for the positive values of x. Here is another advantage of a ReLU function, that its derivative is 1 in the positive part and 0 in the negative part. Now, this is not an advantage that its gradient or its derivative is 0 in the negative part. Due to this reason, it may enter into a vanishing gradient problem. Now, in order to solve this problem, that it has a gradient equals to 0 in the negative part, we have introduced another activation function, which is a leaky ReLU function. If we see the leaky ReLU function, it has a small negative slope. It is not exactly 0 for any value which is less than 0. So it has a small negative slope after before x is equals to 0. So here is the definition of the ReLU function. So it will select the maximum value between alpha x and x. It means if x is equals to positive, it will select the value of x. And if x is negative, then it will select the value of alpha x, where alpha is 0.01. So what is the advantage of leaky ReLU then? So here is the advantage of the leaky ReLU. If we see, this is the leaky ReLU function. It is x for greater than 0, and it returns alpha x if any value of x is less than 0. So if we see the derivative, it is 1 for any value of x greater equals to 0. But it is non-zero even for the value of x which is less than 0. That is, its value is alpha, which is approximately equals to 0.01. So in this case, we can see that even for the negative value of the x, the gradient is not 0, but it is a small fraction of a value. So this is the advantage of a leaky ReLU, that its gradient is not 0 both in the positive direction and in the negative direction. And the advantage is the gradient is 1 throughout the positive direction, that is when the value of x is positive. So in this lecture, we learn about the two important activation functions, that is a ReLU and a leaky ReLU function. These are commonly used activation functions in the neural network because they do not enter or they do not create a vanishing gradient problem. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.